Thank you everyone for attending. As I mentioned before, this is NASA's VULCAN code writes Tecplot Sizzle format using TecIO-MPI. Joining me today is Dr. Robert Baurle from NASA Langley Research Center. Rob manages development of the VULCAN CFD code, which is part of the Hypersonic air-breathing propulsion branch. He got all his degrees from North Carolina State University. And I'm Scott Emley, Chief Technology Officer and Director of Research at Tecplot. I've been here for a long time, 28 years, and I've done CFD development, managed the development of Tecplot 360 for a while. So let's go ahead and get started. Today, I will start by giving an introduction to Tecplot's Sizzle technology. Sizzle is the basis for the work, the TecIO-MPI work that Rob has done. And then Rob will take over and we'll talk about the VULCAN code, the primary uses of the VULCAN code, and the implementation of TecIO-MPI in the VULCAN code, and then performance mostly on the writing side that he obtained using TecIO-MPI in the VULCAN code. There's two reasons I want to talk about the Sizzle technology today. The first is that it offers a significant performance gain for large data, especially for those using finite element data. I want you all to know about it so you can take advantage of those performance gains. And then the second is that it is the underlying technology for the TecIO-MPI library that Rob is using in VULCAN. It's important that we understand the Sizzle technology before we get into the implementation. So I always start with the motivation for why people have such large data and why the data continues to grow. And this is one example of why data sets are continuing to grow. So you can see this is a picture taken out of a wing of a 737, and looking at the nacelle. And on that nacelle, the engine nacelle, you see there's a fence up near the front. And that fence is put there on purpose by the aeronautical engineers to control the aerodynamics at high angle of attack. So here you can see another picture out of a wing of an airplane, and the moisture is such that you can see the vortex coming off of that fence. And that vortex travels over the wing of the airplane and will suppress boundary layer separation that would otherwise occur because of the wake of the engine nacelle. And the placement of that fence and the size and shape of the fence is critical in order to get the desired amount of boundary layer suppression. Now, this requires a lot of grid to do in a CFD code, because it requires refinement in multiple directions to a very fine grid spacing. So because of that, we can't yet really on a regular basis add enough grid, and grid will continue to grow as we go forward in time. And it will grow with Moore's law, because that's how much memory and computing power is available in the computers, particularly the large parallel computers. But in addition to that, in this case, for example, a designer would want to try different positions of the fence and sizes of the fence and shapes of the fence, and might do a lot of different calculations based on those parameters: position, shape, size. And that is a parametric analysis, and you may do hundreds or even thousands of calculations to try to determine the appropriate location for the fence. And that sort of parametric analysis is going on all the time. And that also increases the amount of data that needs to be analyzed, sometimes by orders of magnitude. There's the NASA CFD Vision 2030 document. This is a chart from it, their roadmap, technology development roadmap going into the future. So if you focus on the knowledge extraction line, second from the bottom, I'll do that here, you can see that they're talking about data sets growing essentially with Moore's law, being a 10 billion point unsteady CFD simulations by 2020, 100 billion by 2025, and by extrapolation you could expect $1 trillion by 2030. These are probably the largest cases. There will always be people running smaller cases, but we'd expect these smaller cases to also kind of scale along with this, also growing with Moore's Law, though, although they may be an order of magnitude or two smaller in size. So what is on the visualization side, what is driving the performance or controlling the performance? And this is just a really simple view of the visualization pipeline. It starts with reading data off the disk, going through some sort of a network to the computer, CPU, and graphics processing unit, and then generating an image. The CPU, GPU, the computer speed is doubling with Moore's Law every 18 months, especially if you consider the parallelization. Transfer speed is keeping up with that pretty well, although it tends to come in chunks, 1 gigabit per second to 10 gigabits per second. But the thing that's really falling behind is data I/O speeds, which is doubling every 36 months, according to Kreider's law. And that's for hard disk systems. They can mitigate that somewhat by parallelization of the hard disk. And of course, if you can bring in other technologies that don't involve spinning disks. But this seems to be the dominant long-term storage will probably remain hard disk for some time to come. So the impact of disk I/O performance on visualization now, I'm still talking about the reading of the data and loading it into the visualization package and then visualizing. So the disk read performance is growing slower than grid size. The grid size is growing with Moore's Law. The disk read performance is only doubling every 36 months. And so if you just take both of those things into account, you can see that the total time to load the data from the disk into the application is growing over time exponentially. And this is with current visualization architectures. And if you actually extrapolate that out to 2030, the transfer time is not even in the picture. It's a little bit in the left-hand corner. And it's pretty much dominated by the disk read. And so we need a way to get around this bottleneck. What we're calling Sizzle Technology stands for subzone load on demand, and we reduce the amount of data you read from the disk. And you must reduce it in such a way that as time goes on, marching towards the 2030, the scaling of the amount of data that's loaded from the disk is sublinear. So it's sublinear with the size of the grid. And that way you can mitigate the growth in reading time or loading time. And we do this by saving an index data file and loading only the data you need. And I'll show you a little more about that in a second. Here it is. So if you imagine this 2D grid, we don't do it for 2D grids at this point, but it's easier to see it in a 2D grid. So on the left you have a 2D grid and there's a contour line going through it. You divide that grid up into subzones, in this case 16 pieces, and then you index that grid so that you keep a tree of the min-max values for all the variables in those subzones. And then you only have to load, at read time, you only have to load those subzones that are not the dark subzones, only the light-colored subzones. And that's, in this case, that's 5/16 of the total data. For a large volume data set, that may be 1/100th of the data, or even 1,000th of the data. So it dramatically reduces both the memory requirements and also the time it takes to read that data. So that's the basic idea of how subzone load on demand, or Sizzle, works. I want to take just a couple minutes to talk to you about how you could actually create these files. Rob is going to talk about how he does it with VULCAN. So that's the third option there, right from your CFD code using TecIO. But if you aren't using VULCAN, then you can do it with one of the top two. which is load the data into Tecplot and write it out as a Sizzle file, or you can automate that conversion with macros. So let me just show you how you write it out from Tecplot. So you read it in any format you have, except at this point for polyhedral grids. So it works with IJK ordered grids. It works with classic finite elements. That would be, in Tecplot parlance, it would be tetrahedrals or bricks being hexahedrals. So, but if you have a higher, another general polyhedral, it doesn't currently work. So you load the data file and then you write it out. So you just say write data file. It's from the file menu of Tecplot, and you select the subzone, Tecplot subzone data writer, which will create this .szplt file. That's a binary Sizzle file. That can be done in batch. So you just have, for some types of data files, you can just say Tec360 and then the data file names in -convert, and it will just convert those data files into Sizzle. Some types you actually have to have a batch file, or a macro file, I should say. Some of the loaders are a little more complicated, but you can just record that and then automate it and still use the -convert. The advantage of the convert flag, and this is not so much for NASA users because you have a site license at NASA Langley, but for other users that may be listening, the advantage of the convert flag is that it does not check out a Tecplot license key. So it won't take one of your keys, and you can install it on a machine that does not have a licensed server. And as long as you limit your activities to converting files to the Sizzle format, it'll work without the key. And then finally, the TecIO library it's a library of utility functions that can actually write either the classic tecplot.plt file or the Tecplot, the new Sizzle file, the tecplot.szplt file. And there's a couple of options with this. One is the standard TecIO, which is a serial version of the library, so it performs serial output. And then the new one, and this is what Rob will be talking about mostly, I think, today, is the TecIO-MPI library. And it performs parallel output from applications using the message passing interface, MPI, and under the hood it's using the MPI-IO library. So it hides the complexity of that from you. So it's pretty simple to use. And if you are a code developer or anyone who just wants to play with this, you can download the TecIO library from our website. So let's go ahead and transfer this over to Rob. Rob, if you're there.
Yes, can you hear me?
Yeah.
Okay.
Go ahead.
Okay, well, thank you. So as Scott mentioned, my name is Rob Baurle, and I'm work at the NASA Langley Research Center, primarily doing development work on the VULCAN CFD code. And I'll be discussing my experiences with implementing the TecIO and TecIO-MPI libraries into this CFD software suite. Okay, if at the end of this presentation, if anybody wants more information on the VULCAN code, you can find it at this website. And also there's instructions on, if you want to try the CFD software out, there's instructions on how to request a copy of it. Although I should mention that the software is ITAR and it's only available to U.S. citizens. Okay, so the VULCAN CFD code. VULCAN CFD is currently a hybrid structured unstructured flow solver, and its development has historically been driven by the modeling needs of the hypersonic air-breathing propulsion system community, so basically scramjet applications. Some of the unique or sort of unique features of the code include the fact that it supports both full, elliptic, and parabolic, in other words, space marching, Navier-Stokes capabilities. Again, since it was developed primarily for high-speed applications, we incorporated a space marching capability early in its development. We can, in addition to treating flows with standard calorically perfect assumptions, constant ratio of specific heat calculations, we can also handle flows in thermodynamic and chemical non-equilibrium. And we need that because of the hypersonic capabilities and also for our hypersonic flows that we're interested in, and also for combustion applications. And finally, as far as turbulence modeling, I would say most of the users of the code use the software in a Reynolds average framework using standard Reynolds average models. But we do have a whole suite of scale resolving simulation strategies that you can, or models that you can choose from as well for large eddy simulation or hybrid RANS LES simulations. Okay, so I mentioned early on that the code is a hybrid structured unstructured solver, but the unstructured capability is actually brand new and actually hasn't even been released yet. It'll be released probably in a couple of months. So historically, the code's been a pure structured piece of CFD software. And the post-processing pipeline that we have used historically is as follows. We basically have a whole lot of I/O operations in order to get the final volumetric post-processed data files. We start by outputting files in a Vulcan-specific I/O format, and this operation is done in parallel. We then, in a separate utility, we then read those files in and write them back out in true structured grid plot 3D format files, and this is also a parallel piece of software that does that. So this operation is in parallel as well. The reason we have to separate these out really is driven by the fact that we have space marching capabilities in the code, and the data structure that we use in the solver, it's a reduced memory data structure because we only have to store planes at a time when we space march. The plot 3D format did not support that. So that's the reason for having to separate step 2 out, why we couldn't do step 2 directly in the solver. And then finally, a third step is an optional step, but I think most of the users tend to do this, is to, we then read in all those individual plot 3D format files, which are individual files that have been output based on how many grid blocks you used, structured grid blocks you used when doing the simulation, which for a large parallel application can be thousands of grid blocks. We have an automatic partitioner which can partition the grid into small chunks for parallel load balancing. So ideally, we like to reverse map that back to the original block topology so we don't have to post-process as many grid blocks. So that's what that step 3 does. So if you add up the I/O steps, there's a step 1 does a write, step 2 does a read and a write, and step 3 does another read and a write. So that's 5 different I/O applications to read and write the volume files. So obviously this is not a very efficient way of going about things, and as Scott mentioned, the direction that most CFD applications are headed in is larger and larger cases. So we realized for some time that we have to move away from this, and one of the ways we were doing that is to use TecIO. So back in June, we started learning what it would take to implement TecIO into the Vulcan software suite. Basically started in late June of this year, and in about a week I was able to output .plt and .scplt files in a very basic fashion. At this point it wasn't parallel, but I at least was able to output utilize the TecIO libraries to get .plt and .scplt files directly. I then spent an additional week to add supporting logic to take advantage of the partitioned I/O that the .scplt files offer. And this was important for us because this allowed all 3 steps that I described in the previous on the previous slide to be obtained in just one step. Adding this capability in, even without introducing the TecIO-MPI, just doing the partition right in a serial fashion, was very beneficial to us because we now have 1 I/O step replacing 5 I/O steps. And then finally, there was about another week to implement the TecIO-MPI libraries. And the TecIO-MPI for structured grids is a fairly new technology for Tecplot. And I believe I was one of the first beta testers of that. So there was a few issues with getting the CFD code, which is written in Fortran, playing nicely with the TecIO-MPI libraries, which is written in, I think, C++ primarily. But I should mention the TecIO support staff at Tecplot were very helpful and very responsive to questions and issues that I had, and everything's up and running just fine at this point. So basically, it took about 3 weeks to get all of the capabilities listed here implemented in a very large production-level CFD solver. So I was pretty pleased with that level of effort.
Hey, Rob. Yes, thanks for being one of our early adopters on that. Hopefully it'll be. I expect that it'll be easier for other folks to do it now that we've gone through. You've gone through the implementation. We have some other folks working on it as well. So you had mentioned to me once that you were actually thinking of doing this using MPI-IO directly. I might have had an extra I in there, but how do you think this would compare in terms of complexity to implementing it yourself in using MPI-IO?
I would guess probably something close to an order of magnitude for two reasons. One, while I'm very experienced with working with and coding up parallel applications, I have not done anything with parallel I/O directly with MPI yet. So I'd have to, jump on the learning curve for that, and all of the details involved with getting this stuff to work from scratch, I'm sure, is not an easy task. So just being able to interface with libraries where all of those dirty details are under the hood and I didn't have to worry about that was the only reason this was done in a couple of weeks. Actually, the parallel I/O step 3 here was only a week. So, but yes, it was. I'm sure it was. If not an order of magnitude, if it wouldn't take it would take up to an order of magnitude more time probably to. Well, that long. Say probably 6 months, 7 months, or something to do everything by scratch, I would imagine. So, just to illustrate what sort of performance we're getting out of these libraries, I picked what's probably a fairly large case by our standards. 100 million cell case was selected, which involved a hybrid RANS LES simulation of a model cavity flame holder, and I've just included a pretty picture on the bottom that shows the flow structures that we're capturing with the solver. And just some more details on what we're outputting. For this case, I chose to output 19 flow variables, which means 22 variables total were output if you count X, Y, and Z. Again, this is not a pure arrow code, so typically if you want to, it can be difficult to compute auxiliary variables inside inside of Tecplot itself, because we can't use simple constant gamma relationships in relating the flow variables. So typically we output each independent flow variable that we want to analyze directly from the solver. In the upcoming slide where I show timings, I've got two columns that have serial timings, and I wanted to clarify what I mean by that. Basically, the serial timings correspond to, I'm actually running the source code in parallel, but I'm doing all the I/O in a serial fashion. So I'm basically passing all data that does not reside on the master process. It has to be passed to the master process so that the master process can do the I/O. So it's basically a master-slave paradigm for that purpose. And then finally, I'm going to show for the TecIO-MPI timing column, I chose to, again, I took advantage of the partitioned I/O capabilities of TecIO, and I used the libraries to output the grid was partitioned into 3,308 blocks, so lots of little blocks, and I used the partitioned I/O capability of .szplt to merge those into 100 grid blocks, which was the original grid topology prior to partitioning for load balancing. And again, I just wanted to remind you that this being able to do this with the TecIO libraries allowed us to remove several post-processing steps from the original VULCAN post-processing pipeline. And so here's the performance of the TecIO library. I did a series of simulations ranging from 8 cores to 1160 cores. The efficiency column is just a parallel efficiency value that gives you a feel for how well the blocks were partitioned. So it's basically a measure of how even the cell count was on each processor. So as you can see, it's pretty well load balanced all the way up to 1160 cores. And then the last 3 columns compare the timing information for using the TecIO libraries. The last 2 columns correspond to the serial timings, which, as I mentioned earlier, was a master-slave paradigm. And the middle column there, the SZL MPI, is the TecIO-MPI timings. Well, one thing you'll notice is that the output of the .szplt format is, in general, more expensive than outputting just the standard .plt format. And it's my understanding that's because of all of the indexing they do in order to make it more efficient once the data is loaded into into Tecplot to post-process more efficiently. So basically, you're paying for that efficiency a little bit up front when you output the data files. However, if you use the TecIO-MPI, so if you do the output in a parallel fashion, then you can see that the break-even point appeared at about 36 cores. So at 36 cores, I was able to output the .szplt format in about the same time as I was outputting the .plt format in a serial fashion. And also keep in mind, again, the .szplt also did all of that block merging for me, which I can't do with the .plt format. So the .szplt file that I get at the end of the day has 100 Tecplot zones in it instead of 3,308 that the .plt file would have. Now, unfortunately, the parallel I/O started to saturate at around, say, 145 cores, looks like. And I really didn't get any substantial speed up beyond that point. But at the end of the day, after even once it saturated, the speed up was almost a factor of 3 over the .plt format I/O, and it was more than an order of magnitude faster than the serial output of the .szplt format.
Did you do any test loading the szplt files into Tecplot?
I did in a very loose sense. I didn't, time it per se, but I was just checking it out. This case isn't really large. It's 100 million cells, not a billion cells. Yeah, I didn't notice a substantial difference in load time, but it was faster, the szplt.
Yeah, so just for the listeners' benefit, our experience with other cases is that for IJK ordered grids of 100 million cell size, you may find it, say, animating through 100 time steps to be up to a factor of 3 faster for IJK ordered grids. It's much faster with finite element grids. That's where it really shows a big difference. But you do also see a reduction, significant reduction in memory usage. So if you're memory constrained, you're running on your small laptop or something, that you'll see a benefit. So good. And you mentioned to me that you had actually gotten an idea of what it took to do the plot 3D timing, the plot 3D output for this case.
Yeah, that took about 3 minutes. So that was a little bit slower than the serial.plt format. And,
okay.
and again, that's because the first, as I said, on that post-processing pipeline, the first 2 steps are in parallel, so they were pretty quick. But the last step was serial, so that's the bottleneck. So it basically scaled pretty well with the serial.plt column here, but a little bit slower though. Okay, so this is basically it in the summary. So again, I spent about 3 weeks implementing the TecIO libraries, and that included the time to button everything up as well. Everything's buttoned up. It's in the it's accessible through the Vulcan input file and all that good stuff. TecIO support staff, they were very helpful. I wouldn't have been able to do this in 3 weeks without their responsiveness in with answering questions that I had, particularly early on in the implementation. Again, I've mentioned this several times, but it's really important for what we do, at least with Vulcan. The partitioned I/O capability was very useful to us, even without the parallel TecIO-MPI implementation, since it allowed us to remove several pieces of software that we had to use downstream of the initial post-processing part of Vulcan. So that we could basically throw away a couple of pieces of code because we implemented these libraries. And I should also mention that we didn't make any attempt at trying to tune the MPI-O performance on the Pallades supercomputer that I use for these timings. It's well documented that the MPI-I/O performance is, if you really want to optimize it, you've got to tune it for the particular machine that you're running on. So it's quite possible that the timing information that I showed here could be improved if we took the time to go under the hood a little bit and tune the parameters for our Pallades cluster. And I think that's all I had.
Thank you, Rob. And we have time for questions. When do you think Vulcan might be released with this new I/O capability?
Actually, I can release. It's in the trunk of our revision control software now, so anybody who requests the code at this point on would have that capability. It's in there. It's just I haven't officially released the next version, and so the documentation on how to invoke it within the solver is not included in the manual at this point. There's not a whole lot of it. It's actually a one-liner. So if somebody requests the code and wants this capability, they can just shoot me an email and, hey, what's the input for this, and I can tell them. So the short answer is it is in the code, and if you make the request for the code right now, you will get this capability. I just haven't. I don't update the documentation until I have a formal release of a complete new version.
Okay. How often do you have formal releases?
It's not on a direct timetable. It kind of depends on, we're constantly adding things, adding new capabilities, and as I mentioned, this next release, which we expect in a couple of months, is going to be a major release because we've added an unstructured capability to the code. So when we release a new version is driven by when we think it's a good time, that we've added enough to it that it's a good time to release release it again. So it's typically about every year and a half is about the time frame of when we release new versions.
I'm curious, when you have this unstructured capability, are you planning to support the parabolized Navier-Stokes with the unstructured capability?
It'll be supported with the unstructured capability, but not. You can't space march the unstructured section. So, like I said, this release of Vulcan will be a hybrid structured unstructured solver. So, primarily because of the space marching capability, we already have the ability to break the problem up into what we call regions. For instance, right now it may be very common if you're trying to solve a scramjet engine flow path that you might do the engine forebody, maybe part of the inlet as space marching regions, and then you would then solve maybe the combustor section as a full-up 3D elliptic region, and then maybe space march the aft engine nozzle to complete the flow path. So in that scenario, you kind of break the simulation up into 3 chunks, space marching followed by elliptic followed by space marching. So if you wanted to use the unstructured capability in that scenario, you could only have unstructured blocks in the middle in the combustor section. So basically, if you want to solve the unstructured block, it has to be in an elliptic region. If you want to space march a portion of the flow, that portion has to be structured.
Does TecIO need to be installed in order to use the batch mode converter? The answer is no. That is, the conversion is actually built into Tecplot 360, and so you don't need TecIO. It's already there in the code. Did you try stripping the directory for the Luster file system to assess performance on PFE? Rob is not able to answer the question at this moment. He will respond to this by email later, but my understanding is that Rob just used the default file system on the Pleiades, on NAS. And so my guess is he didn't, and he stated this, he didn't try anything special to improve the file system performance. And the next question is what file system was used, and again, it's the default file system on NAS. I believe it is a Luster file system, but I'm not an expert on that. But it is the default file system. So that concludes our presentation. Thank you for attending the webinar. The recording will be available by November 5th at our Tecplot website, tecplot.com/webinars. We have other webinars there as well. And if you have questions directly for Rob, his email address is there, and then myself, Scott Emily at tecplot.com. So thank you again,